works. It makes me nervous.
I think it basically records a 1 minute segment and then uploads that to like ChatGPT so you can ask questions.
Okay, we don't need to graph R. Are we good? It's an ellipse. Okay, so X is 2U. Y is 3V. Oh, we are doing multiple integrals, change of variables and multiple integrals. Okay, so this is 36u squared plus 36v squared is 36. So u squared plus v squared is 1. So this is our region S now in the UV plane. It's just a good old unit circle. Radius is 1. Good? So, let's set up. We have this double integral over R. We need to find the Jacobian. So del xy del uv is going to be determinant. Del x del u, del x del v, del y del u, del y del v. So what do you have for del x del u?
2.
Del x del v?
0.
Del y del u?
0.
Del y del v?
3.
Good. And then this is going to give us 6. If you have a matrix that's fully diagonalized, meaning there's only entries on the diagonal and zeros everywhere else, the determinant is equal to the product along the diagonal of all of the entries, even for bigger one, like 3 by 3, 4 by 4. Fun fact, before you take linear maybe. Okay, so there's our Jacobian. So then now x squared is going to become 2u quantity squared, right? And then what is dA? Well, we have absolute value of our Jacobian, which is already 6, positive. And then I'm just going to put du dv. Oh, that looks so ugly. Hold on. I'm writing so jiggly. Du dv. So far, so good? I didn't set up limits of integration. If you do it in the UV plane, that's like the equivalent of being in rectangular if you keep it du dv. But it's a circle. Why would you do that? It's going to be ugly to work with. So now from here, let's go polar from the UV plane. Okay. So then what does that mean? All right. 2 squared times 6. Let's take the 24 out. Okay. Then you can think of it like this is going to go 0 to 2 pi. Limits for R would be 0 to 1. And then we have this u squared here, right? Well, look at where u is. It's basically where we normally see x in the xy plane. So if you transform that to a polar coordinate system, u would be equivalent to, which is in polar, there you go. So r cosine theta, and then we have it squared, don't we? And then du dv gets replaced with what? r d theta. So we kind of changed coordinate systems twice. Do you see that? We went from xy to uv, picked up a 6, and then from uv we decided to go polar, picked up an r. Okay. From here, do you need me to keep going? You got it.
I was just having trouble. I didn't see when you multiplied it out.
When I multiplied it out?
So like,
oh, at the very top?
yeah, at the very top.
Oh, to graph S.
Yeah, that's kind of what I got stuck on.
Ah, okay. Applying the transformation.
Yeah.
That's a crucial step. Okay. We all right? Yeah. Oh, 21's a cute one. No, you guys don't like it? Well, Roy, I know you don't like any of them. Has there been a single problem you like that we've done all semester? No. See? We knew that. We knew that. In fact, I would be so bothered if you actually enjoyed one of these for once. Just keep it up. Okay, double integral over R, xy, dA. R is the region in the first quadrant bounded by y equals x, y equals 3x, and the hyperbolas xy equals 1, xy equals 3. And then they tell us PS, let x equal u over v, and let y equal v. That's going to be our transformation. Okay, so let's graph all this. We're in the first quadrant. And it looks like all the action's going to happen between 1 and 3 pretty much, right? So 1, 2, 3, 1, 2, 3. Okay, y equals x. We know what that looks like. Slope is 1, goes through the origin. Y equals 3x, slope is 3, so rise 3, run 1. So far, so good? Okay. X times y equals 1. You're probably used to seeing it as y equals 1 over x. And then xy equals 3, y equals 3 over x. Doesn't matter. The nice numbers to plug in for x are 1 and 3, right? Okay. So let's do y equals 1 over x. If x is 1, y is 1. And then if x is 2, y is a half. If x is a half, y is 2. So let's just say it's like right here-ish. Y equals 1 over x. And then y equals 3 over x. I need another color. This is good. Okay, so we'll have, if x is 1, y is 3. If x is 3, y is 1. So it should just be higher up. Yeah? So this is y equals 3 over x. Or xy equals 3. So can you see the region? It's right in here. And yeah, I mean, if we were to integrate over this region, ew, right? Ew. Okay, so we have 4 different curves bounding the region. So just number them. I did it this way. R1, R2, it doesn't matter. R3, R4, okay? So now we're going to apply the transformation, figure out what S1, S2, S3, S4 are, graph S, and then hopefully it's a nice integral. Find the Jacobian, blah, blah, blah. Okay, so here we go. R1, let me call it what they called it. XY equals 3. So just start applying the transformation. I'm going to replace x with u over v. Let me also replace y with. So this gives me u equals 3. So that's S1. Good? Okay, R2. What's R2? Y equals x, right? Okay. So y is v, and x is u over v. So what does this give me? Good. V squared equals u. This is S2. Okay. Now, u-axis goes in the direction the x-axis is. V-axis is in the direction y-axis is. Always alphabetical order. So this is kind of like if you had a parabola y squared equals x. So it's opening up to the right. Does that make sense? Shall we remind ourselves just in case? The new variables might give us a run for our money, right? You don't want to get all jumbled in the brain. It can happen. R3. R3 is xy equals 1. So then it'll be the same as S1, right? You'll just end up with u equals. Very good. Am I skipping too many steps? Are we okay? Mustafa, what's up?
Do we always keep it like v squared equals u? Because like I thought like you can like square root it and have u equals.
We will in a minute because you don't need the bottom half, right? But I just left it until I graph it all to see. Do I want the bottom half? Do I want the top half? I would.
Like,
Yeah. Yeah, I mean, I can already tell though you're only going to use the top ones because these are positive, right? I don't know. He wants to square root it. I'm saying let's wait. Yeah, let's wait. You're making me nervous. Don't do that.
Two segments. Use the top one.
Yeah, well, the bottom one won't be relevant to enclose. And then,
Really?
no, it will actually.
It will.
So we chose it because we're using the quadrant 1 portion. Because, yeah, this technically, you know what 1 over x looks like. It's here and here. That's right. That's why. Is that why you wanted to get rid of it
No,
already?
like I did it, but then I forgot. Like I realized like I did that.
Okay, because they told us we're in quadrant 1, then we're only using the positive portion of this graph. So yeah, if you want to already say, oh, then we're going to have to deal with the positive portion. No, because the lines would cut.
They will cut top and bottom.
It said first quadrant in the book. It did say first.
Yeah.
Oh yeah, guys. Oh, otherwise, what? How would you know what's going on? Most certainly. You would need to. Yeah. Why would they do that? Yeah.
Or we can multiply by 2, right? Because we have the same area.
Right. Okay, so this ends up being v squared equals 3u. Yeah? You need me to do it or you're good? You're great? Okay, v squared equals 3u. Okay, so let's graph it now. And yes, we've determined we're also in quadrant 1, not 4, because... Okay. Because we used the positive values, right, for the other graph. Okay, UV. Let's see. Same thing. 1, 2, 3. 1, 2, 3. Let's do u equals 3. U equals 1. And then u equals v squared. So that would go through 1, 1 and like 4, 2. Right? This is S2. Should I have been labeling them? S1, S3. And then S4. 3u equals v squared. Then it's just going to go through 3 higher, right? 3, 3, yeah. We'll go through here.
And 1, 3.
Yeah. No.
1,
1 rad 3. So 1 and like 1.7 and 0, 0. Okay. We got it? Okay, so our new region S is right here. Is this better? Yeah, we could set it up with 1 integral, right? So what order looks the best? To do du dv or dv du? Right? U's limits should be constant. So u on the outside, u goes from, and then v goes from, good. How are we? We're good? Okay, now we need the Jacobian. Del uv. Do you remember the transformation? Probably not. Let me write it down. X equals u over v and y equals v. So del x del u. Very good. Del x del v.
U over v squared.
Negative, yeah. Del y del u.
0.
Del y del v.
1.
Okay. So this determinant is
1 over 3.
perfect. Okay. Good. Ooh, it's variable. How exciting. All right. So then we have double integral over r x y dA. Just rewrite the original so you don't lose your mind. So u's going to go from 1 to 3. V is going to go from rad u to rad 3u. Then we have, what was our original integrand? xy. Oh, why did I scroll up? It's right there. xy. X times y in our new coordinate system is u. Then we have absolute value of the Jacobian. So absolute value 1 over v. And then we set it up to be dv du. Right? Because the constant limits were for u, so they go on the outside. Okay, now, do I need absolute value on v? Look where we are. We're good, right? So you can drop them. So then from here, do you need me to help you integrate? We might as well. We came this far, right? Okay, so 1 to 3. And then we're anti-differentiating with respect to v first. So u times ln absolute value of v evaluated from rad u to rad 3u du. Are we okay? All right. And then those radicals, here's something your algebra teacher probably didn't make a big deal about. This symbol is the positive principal radical. Okay. So if you see like square root of 9, that is 3. Not plus or minus 3, that is 3. That symbol means give me the positive principal radical. If I say, what are the square roots of 9? And I don't plus or minus 3, right? Okay. So we have something called the square root property. When you add a square root to both sides of an equation, you need to go add the plus or minus to obtain all possible roots, all possible solutions. But if you see this symbol, this means I just want one. I just want the positive principal radical. So what is this? 5, like that. It's always positive. How do you make it negative? You have to add a negative on the outside of that expression. By default, it is positive. So why am I saying that? Because right here, we're going to have ln. I don't need to put absolute value rad 3u. That's the positive principal radical. So you're just going to have ln rad 3u minus ln rad u. Like, long story to tell you why we're okay to drop the absolute value. You don't need them. Does that make sense?
It's just because you write down the equation rad and you know it's in the first quadrant.
No, just seeing rad means it's positive. If you see the radical with no minus sign
It's a
outside.
rad of any variable, it's just always positive.
Yes. Now, that's why the square root of u squared is equal to, no, absolute value of u. Because what does this give me always? What did I just tell you? A positive. So how do you make sure something's positive? You put absolute value. Because here's what's going on. If you have square root of negative 3 squared, what do you get back? No. 3. Because you square it, it's 9. This symbol tells me give me the positive principal radical. But if I have square root of positive 3 squared, what do I get back? 3. So that's why absolute value of a variable quantity is what the square root of that variable squared simplifies to. Okay?
But x squared equals that, which is plus or minus.
Was there a radical in that equation? No. You went and added it. So to make sure you have 2 solutions, right? X squared should have 2 solutions. You have to add the plus or minus. There was no square root to begin with. If I told you square root of x is 4, there's already a square root. Don't go add a plus or minus. How would you solve it now? You square both sides, right? No, just x. Why am I writing that? Okay. And you're done. So only add the plus or minus if you add the square root. You take an even root of both sides of an equation. Okay. Anyways, back to the problem. 1 to 3, u. And then you don't want this to be right? So you use your log properties, so slick, rad 3u over rad u. Oh, ln rad 3, so painless. What is ln rad 3? It's a constant, so we're taking it out. And then antiderivative of u? Good, from 1 to 3. Even ln rad 3, that's ln 3 to the 1/2 over 2, and then 3 squared, 9 minus 1, right? So that's 1/4 ln 3 times 8, so 2 ln 3. Nice? That's very slick. Okay. So, what was hard?
It wasn't hard. I was just confused. I just wanted to make sure I drew. X
Okay.
correct.
The graphing. The graphing's always a problem. Yes, Seth?
If we wrote it as a 4 ln rad 3, would we still define?
It's not fully simplified. Is that what you were going to ask too? Yes, you have to use your log properties. Good? Okay. That's it. Let's do the practice. Don't forget to like, subscribe, and follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later. Mwah.